Today what we're going to talk about is a little bit about the periodic table and types of compounds. And what this does is sets the stage for us when we begin to identify different types of compounds and be able to write their formulas and name them. So the first thing we need to know is kind of how the periodic table is organized. So it is organized in columns and rows. And those columns we call groups or families. And we call them families because they have physical properties alike, but also chemical properties alike. For instance, I know that sodium, which is in column 1, is a very, very reactive metal. And underneath it, we have potassium, which is also extremely reactive. So like I said, they have characteristics that are alike. And then the rows are called periods. That's where we get our name periodic table from. And the reason that they're called so is because there are regular trends of increasing or decreasing properties as you go across a row. For instance, increasing melting point, increased electronegativity, which we'll study later, but just overall trends when we go across or down in the periodic table. Alright, so we're looking at some different areas on the periodic table. And so the first main division that they do is the representative and non-representative elements. And so the representative elements illustrate a variety of chemical properties, just like we have representatives of our school who illustrate a variety of the type of students that we have. And so these are the group A elements, which is when you look at the periodic table, those are going to be all the tall columns that are labeled 1A, 2A, and so forth. And there'll be a picture here in a second. And then we have the non-representative elements, which are really just a bunch of metals with the same kind of properties. And those are the elements that we find in the middle part of the periodic table. And so here's our picture. So we can see the representative elements are the ones that are highlighted in a light blue color there. And then the transition metals, which are our non-representative elements, are in the center. And the bottom two rows that are underneath that are not on this picture would also be non-representative elements. Okay, so let's look at some other areas on the periodic table. Well, one of the ones that we talk about a lot is the division between metals and nonmetals. So our metals are the elements that are to the left of the staircase, but not including hydrogen. Hydrogen is actually a nonmetal, and we'll talk about why it's actually over on that part of the periodic table later on. Then we have our nonmetals, which are to the right of this staircase that is in the periodic table. And on this particular chart, they're all colored in a yellow color. And then bridging the gap between the metals and the nonmetals are what we call metalloids, which are adjacent to the staircase and include most of those elements. It doesn't include aluminum, so you need to make sure that you know that. It also doesn't include polonium, but that's not anything I would actually ask you to recall. So let's talk about what a metal is. And I think most of y'all know what a metal is when you see one, is that we know it's shiny, they call it metallic luster, that it's dense, and that it's conductive to both heat and electricity. So I went back to the storeroom and grabbed some zinc. We just have some back there in this lovely little labeled bottle. And I poured some out into my hand here, and you can see it's, pretty shiny. It's gray. If you try to bend it, it does bend. It's actually a little bit difficult to bend. It's really strong, but you can bend it a little bit if you put some strength to it. I also did plop that on the balance, and that little sample that I had there weighs about, we'll say, 6.4 grams. And we're going to use that for comparison here in a second. So next we have our nonmetals. And so the nonmetals are pretty much everything that a metal is not. And so metals are shiny, so nonmetals are going to be dull. We know that metals, we can make them into a variety of shapes, that they're malleable, we can flatten them into sheets or ductile, we can stretch them into wires, but nonmetals are brittle. If we try to do any of those things with there, it has a tendency to crumble and not make really anything that we can construct stuff with. And then also in general, they're going to be non-conductive to both heat and electricity. So again, I kind of wandered back to the stockroom and got a sample of sulfur. I have this gigantic bottle of sulfur back there, so I can plop it open for you. And when we look inside, we can see that kind of looks like yellow chalk. It's a little bit waxier than that, but you can see there's lots of little pieces in there from when people have handled it in the past and have broken it. But it's certainly not anything that you could make into a wire or a piece of foil or anything like that. And so then the last group, which we already kind of mentioned, was the metalloids. And so, what is a metalloid? Well, it doesn't really actually quite fit into one group or another. A metalloid is something that has properties of both metals and nonmetals. And there's kind of a trade-off in between. Maybe it's something that's shiny, but it's not particularly conductive. Or maybe it does have those conductive properties, but it's actually brittle. And so I wrote a couple examples down here of arsenic and silicon. And so back in the storeroom again, I found a sample of silicon. We actually have that in a jar as well. And you can kind of see even from looking from the jar that it is kind of shiny. So I did dump some out in my hand. And I don't know if you can see or not, but there's some dusty pieces, little pieces, almost look like sand in my hand. And those are the broken chunks of silicon that are inside that container. And I can tell you, it really is it's kind of crumbly. I mean, yes, it stays together, but it feels more like glass than it does like a piece of metal or something. And so again, I plopped that on the balance as well, just to kind of give you an idea of what that looks like. Oops, let me back up here just one second. There we go. So it weighs about 3.6, and you can see this chunk is relatively actually the same size as the amount of zinc that I put on there. If anything, it's bigger, but it weighs half as much. So again, we can see that it has a non-metallic property of having a low density. So we take all of these things and they actually do form compounds. They go together. So let's figure out how. So to form compounds, we know that elements have to bond. Makes sense. Bonding occurs outside of the nucleus and involves the electrons. And we'll learn more about this later on, but it could either involve a sharing of electrons or a transfer of electrons, but some kind of electron business out there. And then it says in some cases electrons are transferred and an ion forms. And so we have a couple of different ions here. And so the first kind we have is an anion, and that is how you pronounce that, is anion. And so what an anion is a negative ion. And let's think about that in terms of electrons. If I'm a negative ion, I am going to have to gain electrons, right? Those electrons are negative particles. So when I gain those electrons, I become negative. Now, when an atom gains those electrons, the name of it actually changes, and we change the suffix ending of that element to IDE when we do have an anion. And some of those might sound familiar to you, so things like chlorine. Chlorine can form an anion, and so we call it chloride. Or fluorine can form an anion, and we call it fluoride. Or oxygen, and we call it oxide. So those are just some of the examples. And then we have cations, so that's why we have Hello Kitty over there. So a cation is a positive ion, and it is formed when an atom loses electrons. Common misconception is students want to say, oh, it gains protons, it gains protons. Well, if it gains a proton, you've changed the element that it is, like hydrogen, which has one proton. If it gains a proton, it becomes helium, and it's not hydrogen anymore. On those ones, we do not change the suffix at all when it's formed. So an example of hydrogen, when it forms an ion, we just call it a hydrogen ion. We don't do anything to its name. A way that you can remember cations and anions is to remember cats are good, which people tell me that they're not, but that's what I like to think. Another way we can do it is by looking at the word cation itself. If you'll notice in the center of it, it does kind of have a positive sign in there, right? All right. This next slide gives us some examples to work through, and you have some of these on your worksheet. So the first thing it's asking you to do is tell whether each ion is a cation or anion, or neither, and then tell the number of electrons gained or lost, and then lastly name the ion. And I'll try to write them in there, but then I'll also put the actual screen up so you can read them. So the first one, let's see, it's a positive sign, so that makes it a cation. Number of electrons gained or lost. So since it has a positive sign, it has to have lost, so we'll say lose 1 electron. And then the last thing we need to do is we need to name it. So it's going to just be named sodium ion. Okay, so the next one's also positive charge, so that's a cation. It's got a positive 3 charge, which means that 3 electrons were lost. And its name is an iron ion. It's kind of fun to say. All right, so the next one is a negative charge. That makes it an anion. So negative 3 means that it gains 3 ions. And so the name of it we have to change, because anions we change the ending to. So it's phosphorus. So I'm going to go with phosphide, right? IDE, phosphide ion. Okay, and the last one, we also have a negative charge there, which makes it an anion. And it's just got a negative sign out there, which means 1 electron lost. And then its name is fluorine, so we need to change it to fluoride ion. And so there it is, so you can read it. Alright, so the next thing we're going to do is we're actually going to look at a bunch of different compounds and make some observations about them, and I will pull this table back up towards the end so that you can kind of see some of the different things that I wrote down. So when we start looking at different compounds, let's see what we got here. We got carbon dioxide, which y'all probably already knows what it looks like. So I blew some air into the balloon, which is not all carbon dioxide, but it's about, I would say, 14% carbon dioxide, and I let it squirt out of the balloon, and we can see that carbon dioxide is just what you thought it was. It's a gas, and is indeed colorless when we empty it out of there. The next one on our list there, we have sodium bicarbonate, which you guys know better as baking soda, which again, you've probably seen before. You've probably looked at it at the cabinet. And so I found some in the storeroom and peeked in there, and it looks exactly like you thought it does. It's a white powder, not particularly crystally, but definitely a white powder. Next one we've got is CH3OH, which you have seen before in class when we did our safety training. I pulled this bottle out, a big gigantic flammability hazard on the side there, but this is methyl alcohol, and as you recall, it's a liquid in there, just a nice clear liquid. NiNO2 is nickel nitrate, and so inside the jar we can kind of see it's a green crystals, a lot like the copper chloride we used the other day. Then C12H22O11 is sucrose, which you guys know better as sugar, so it's kind of a little bit silly to look at it, but there it is. It's lab sugar. Looks exactly the same as the sugar you have at your house. Next one is NaCl, which again, you already know. That's sodium chloride, which is table salt, except this is fancy lab salt. So again, I open it up and it looks like just what you expect it to. White crystals. The next one I have is C3H7OH, which is isopropyl alcohol, or what you guys call rubbing alcohol. And so you're used to seeing that, which is again is kind of a clear liquid. And then I have Ki, which stands for potassium iodide. And so we'll go ahead and open that up, because you probably haven't seen that before, but it's kind of a white crystal. Looks a lot like salt does, maybe a smidge yellow. And then the next one we have is CaCO3, calcium carbonate. And that, when we open it up, it looks like rocks, and it looks like rocks because it is rocks. It's actually marble, which you guys have probably have seen. They use it for decorating gardens and that kind of thing. And then the last one we have is H2O, which is kind of silly here, but I went ahead and grabbed a jug of distilled water just so you could see that water is clear, and it's a liquid. So when we start to put that stuff all together, and you may need to pause this slide here, we can kind of start seeing some patterns emerge. You know, we've got gases, we've got liquids, we've got solids. When we start to look at it a little bit more closely, let's kind of look at some of those solid things there. We have this one and this one. I think that's all. Oh, one more. Let's start looking at the elements that they're made out of. Sodium is on the left side of the periodic table, so it's a metal. And chlorine's on the right side of the periodic table, so it's a nonmetal. Potassium's on the left, which is a metal, and the iodide is a nonmetal. Calcium's on the left, it's a metal. The carbon and the oxygen are on the right-hand side, so those are some nonmetals. Sodium's on the left side. HCO3 is on the right side, and so it's nonmetal. And then this one here, nickel is in the left side. It's kind of in the middle, but on the left side of the staircase, so it's a metal. And then N and O are on the right-hand side. Those are nonmetals. And let's see, carbon is on the right-hand side, so that's a nonmetal. And then we've got some more nonmetals after that. Well, looking at most of them, we can see if it's going to be a solid, it is probably going to be made out of a metal and a nonmetal. I mean, we have one that doesn't work there, but pretty much everything that's solid is made out of a metal and a nonmetal. And if I had to guess what color this thing was going to be, I would guess probably white. I mean, yeah, we got this green one here, right here, but pretty much they're white. Okay, well, let's look at the gases and the liquids. Let's see, this is a nonmetal, and oxygen's a nonmetal. And these are C's and H's and O's and H's, and they're all on the right side, so we got lots of nonmetals there. C's and H's and O. Okay, those are nonmetals. And water. H is on the left-hand side, but it's a nonmetal and a nonmetal. Okay, so if it is a liquid or a gas, it's probably going to be a nonmetal and a nonmetal. And if I had to guess what color it was, I would say it actually doesn't have a color. So colorless is what that looks like. And so what this gives us is the ability to figure out really the two different types of bonding that we have. We have bonding that occurs between metal and nonmetal, and we have bonding that occurs between nonmetals and nonmetals. And this helps us to distinguish between the two. So, how we break them up is this. We have ionic compounds. Ionic compounds are the ones that are made out of a metal and a nonmetal. Ionic compounds are very strongly bonded. And that means that they're also going to have very high melting points. They're going to be crystalline solids. They are probably going to be white. And what we call the smallest particle is we call it a formula unit. Now, are there exceptions to this? Sure. You know, the nickel nitrate was green, the copper chloride used in class the other day is blue, so there are lots of different examples that may not be white, but they still are very, very strongly bonded and made out of a metal and nonmetal. The other type of compound is a molecular compound. And so molecular compounds are made out of two or more nonmetals. They are weaker bonding than ionic compounds are. Because they're weaker, they're going to have lower melting points, which is why they are either liquids or gases at room temperature. In most cases, they are going to be colorless. And the smallest particle is called a molecule. Now again, there are some exceptions. We had sugar. Well, sugar's made out of nonmetals, and it's definitely a white, and it's definitely crystals. So, how can that be a molecular compound? Well, if we think about it, and we heat up sugar in a pan, it's fairly easy to melt that. That's how we make candy such as cotton candy, or melt it down to make lollipops, things like that. And if we try to melt salt, which is an ionic compound, there's no way we're going to be able to melt that in our home because it requires much, much higher temperatures. And then again, are they all colorless? Well, no, not necessarily. There are some gases that have brown colors and yellow colors and even purple colors. And so just in general, they're going to be colorless. So I hope this gives you a good introduction to the different types of compounds and the parts of the periodic table, and we will talk more about this later on.